Good morning. In yesterday's class, we looked at interference, and specifically we took the case when you have two beams interfering, and we arrived at this expression. And we looked at the various terms. So, we said I naught is a term that relates to the individual intensities. So, you have two beams interfering, and I naught relates to the intensity of each of those beams. In fact, it is nothing but the sum of those intensities, and gamma relates to what we call the visibility or the modulation depth of the fringes. And we looked at how, if you want your fringes to be very clear, you need to have a large modulation depth, and surprisingly that meant sometimes throwing away intensity, because you need to make both the beams have the same intensity. With the beam coming from the object, you can't always control the intensity, you may lose a lot of light, and therefore you end up having to reduce the intensity of the reference to make them more equal. And having more equal intensities will improve your modulation depth. In other words, improve this difference here between the peak or the high intensity and the trough and the low intensity. In the ideal case, this should be the maximum intensity possible that you can achieve with two beams that are interfering, and this low point here should actually be a 0 where you have perfect cancellation. So, you have perfect destructive interference, and then your modulation depth is 1 because you are going from an intensity of 0 to the maximum intensity from these two beams. Okay. We also looked at when you look at two waves interfering, how from the fringe pattern you actually get an idea of the shape of the wave, right. So, we said for the patterns that are shown here, you can imagine that this was created by a plane wave front and a tilted wave front, whereas this was created by maybe something like this, a spherical wave front and a plane wave front. And the fringes, and to be more specific, let us say wherever you have constructive interference, they indicate the path where the optical path length difference has one value, and clearly the way that optical path length difference is varying is what you can see in the fringe pattern. Okay. So, up till now what I have drawn are free space interferometers. I just want to tell you that you could also have a fiber interferometer. So, you have light travelling within the fiber. The principle is exactly the same. If however you needed to measure some sample, you would have that part in free space, because obviously the light has to leave the fiber, hit the sample, reflect off the sample, and then re-enter the fiber. So, this is a Michelson interferometer. It does not look like a standard Michelson where the mirrors are perpendicular to each other, because here you are creating those two paths in fiber, and you can align the fiber in any orientation, it really does not matter. What is important is that this reflector is aligned such that most of the reflected light, or a lot of the reflected light, will couple back into this fiber and travel along this path. So, here you have the light incident onward light. This is a device that will split it into two parts. One arm allows the light to leave the arm and hit the object that we are studying, the object of interest. The scattered or reflected light from this, some of it will get captured by this fiber, return. Here you can have a mirror, and you can actually have a mirror pigtailed directly onto the fiber, so you never leave the fiber. Light comes back, and then these two combine, and you can study this again with a camera or photo detector. Okay. Now, just to reiterate, there are many different kinds of interferometers. The previous one was a Michelson. This is a Mach-Zehnder. So, here again we are creating two beams of light, but you are doing that with a beam splitter here and a beam splitter here, so that in this interferometer no beam traverses the same path twice. So, in the Michelson, it goes up to the mirror and then it traverses that same path again. Here this beam gets split by the beam splitter, it travels to this mirror, travels onward like this, and then travels to the detector. This one travels this way. Okay. Again, I might introduce a slight tilt, so that if this is one beam falling on the camera, the other arm is tilted slightly, so that this is how it overlaps, and then I am going to be seeing fringes in this region here. Okay. The fringes are going to be in the region of overlap. Why is this interferometer of interest? Well, I could, for example, put a glass cell here and fill this glass cell with different liquids, and then depending, so I will do a reference measurement where the cell is empty and I look at the fringe pattern, and then I fill that cell with the liquid of a certain refractive index and I look at the fringe pattern, and from the difference I can extract information about the refractive index. Or I could have a transparent block that is sensitive to temperature, and as the temperature changes, either that block expands or contracts, so its length changes, or its refractive index is a function of temperature, and then again the fringes are going to change from one temperature to another, and I could use that as a sensor. So there are many different ways that you could use this as a sensor, right? Why do you want to make such measurements with an interferometer? Well, if you think about it, what do you think is the sensitivity of your interferometer? What limits the sensitivity? It's the smallest kind of measurements I can make. What is the resolution? Yeah, in a sense. Of my interferometer. What will limit it? Is it only he says it's the resolution of the detector. Is it only suppose I give you the world's best detector. I give you a detector that's not even been invented yet, and it has super small pixels. Is it only limited by the resolution of the detector? What do you think limits? When I ask you these questions, always, if it's optics, you can almost always convert this question to a question about phase. Okay. So if I'm asking you about how sensitive a measurement this is, how sensitive a measurement of phase is what I'm asking you. And what's the problem with phase, with these phase measurements? Remember your intensity equation, your interference equation. What is your interference equation? I1 plus I2 plus the visibility or modulation depth into a cosine. What limits? So you're really interested in that third term. What limits anything which is a cosine? Say I have a phase difference. I think we had this discussion yesterday. If I have a phase difference that relates to a length difference of lambda, and I have a phase difference that relates to a length difference of 2 lambda or 3 lambda or 4 lambda, can I really make out? I can't, no? So finally it's lambda that matters, and actually it's lambda by 2 that matters. So in a sense, of course, that assumes a detector can detect that, but that's usually not the limiting case. The limiting case is that 2 pi, 4 pi, 6 pi, 10 million pi to an interference pattern look always the same. Okay? So that's my limit with interference, that I'm limited to measurements in terms of lambda or really lambda by 2. Okay. So if I have a change in length, say I'm using an interferometer to measure a change in length, and the change in length is lambda, or the change in length is 2 lambda, I can't tell. I can tell that there's a change, but I can't tell whether it was lambda or 2 lambda or 3 lambda or 4 lambda, right? So that's my limitation. There are ways to get around it, right? I could use two wavelengths. Then something happens for lambda 1, something happens for lambda 2, and if I can sort of create an effective lambda, which is a function of lambda 1 and lambda 2. So there are many ways to get around that. But if at the most basic level, that's my constraint. Okay. Okay. So let's say I wanted to measure height. How would I do it? I have available to me, the information that I have available to me is the intensity that I am measuring. And again, I am saying this, I am always writing it out like this. Please note, it is always that I am measuring this. Okay. So I have a camera image of an interference pattern. It gives me the fringes, so the points of constructive interference, the places of destructive interference. I have that information. Now say I wanted to measure a height. So I have not drawn the whole interferometer here. I am just showing you the last part of the sample arm and the last part of the reference arm. The reference arm, the beam comes, hits the reference mirror and reflects back. In the sample arm, what we initially do is have the sample beam or the investigating beam fall on one region of the sample. So my sample has a step in it. And initially we align the system so the beam falls here. So it hits this part and it reflects off this part. And that travels back, and I can capture that interference pattern, and that's what I've written here as I1. Now I move the sample so that the beam falls here. So I can either move the sample or I could move the beam, doesn't matter. The point is my second reading is to have the beam fall at a different position of the sample. Okay. If I do that, I will get a different interference pattern. Why? Because the path length of this beam is different from the earlier case. Okay. So now I have a second one. Now I0 doesn't change. Why does I0 not change? I0 and gamma don't change. Why not? I am using the same two beams, and I0 and gamma are functions of those same two beams, right? What has changed is delta. The phase has changed. So now I have these two equations, or I have these two intensity distributions. What I am interested in is finding not delta 1 or delta 2. I want to find out the difference in optical path length. So delta 1 relates to the optical path length seen by the beam in the first case. Delta 2 is the optical path length seen by the beam in the second case. And if I could somehow get this information and take the difference between these optical path lengths, I should be able to extract height from that. Agreed? In fact, this is not right here. Actually, it's OPD1. OPD1 is this distance. So, and this is the first case. So the difference here gives me twice 2h actually, right? So I actually should have a 2 here, I think, right? But you get the point. It's the difference that I need. Now the problem is, I have this intensity I1, the distribution, I have I2, I want the deltas, but I don't know I0 and I don't know gamma. Can you think of some way we could solve this? I have this is a known, I want this, these are desired, right? But I don't know this, I don't know this, I don't know this. Is there any way to solve this? Sorry? I can't take a ratio here because they are buried in a cosine and so on, right? And it's not just, AX and something. AY or something like that, right? It's not a simple expression. So the problem here is I have more unknowns than knowns. Right? Now, if I had as many unknowns as if I had as many knowns as unknowns, I could solve this. The problem is I have more unknowns. So I am going to do some more experiment, get some more data so that I get more knowns. How can I do that? Well, I don't know I0 and I don't know gamma. And you might ask, I'm surprised you're not asking, well, can't I just measure them? Can't I measure I1 and I2? The thing is, in a practical system, you can measure the intensity you're sending into the system. Once it goes inside the system, splits, reflects, to get an accurate measurement of that is really very hard. May not be easy for you to put some device inside and measure what is that actual intensity falling on the detector. So it's not practical. You're not going to get accurate results if you try to go and measure I1 and I2, right? So you don't want to go by measurement of I1 and I2. You don't want to calculate I0 and gamma in that sense. But what I can do is this. If somehow I can introduce a known phase change, okay, then I can make another measurement. I haven't changed the intensity of the beams involved in the interference, but I am introducing a known phase change. So how do I do that? This is called phase shifting interferometry. So my standard interference between two beams gives me this expression. Now let's say, and as we know, the unknowns are I0, gamma and the desired phase delta. Let's say I introduced a phase change. That's going to change this equation by this phase term appearing here. Yes? I haven't changed I1 and I2, but I've somehow introduced a known phase change. How could I do that? How could I introduce a known phase change? An additional phase change. So using not a known sample, I mean, even if you say known sample, I want to keep my setup with my sample. I don't want to remove the sample and put another sample. That will change things, right? The beam coming from the object has to be the same. I'm just adding an additional phase. I'm not taking away the object beam. Remember, I1 is the beam coming from the object. If I take away the object, it's not I1 anymore, it's a different value expression. So let's say we had the Michelson, so that's my source, beam splitter, this is my reference mirror, and here let's say is my sample which is reflective. What is reflecting and coming is what I am calling I1, and this is I2. Now, if I remove this and put a known sample, that's a different I now, because it will be having the properties of that reflector, not of this sample. So I don't want to change that. I am not changing I1 and I2. If I do that, then I0 is not constant anymore in the equations. I make my life even more complicated. I want to introduce an extra phase. How do I introduce an extra phase? Sorry? So shift the reference arm. In other words, how can I introduce phase? I can introduce phase by introducing path length. So all I do is move this mirror. If I move the mirror, I have introduced an extra path length. The path length difference will change by, I've moved it a certain amount, that's twice that length. And let's say it's in air, so I don't have to worry about refractive index. Then I have 2 pi by lambda into twice the distance I've displaced the mirror. That becomes an extra phase, which is in one arm, not the other arm. So I have an extra phase difference now. So if I make a measurement now, so I have I1 which is this measurement, and I do this repeatedly, I can now get 3 equations. I have 3 unknowns, but I have 3 equations, 3 knowns, and then I can solve it, right? I need to have at least that many equations as there are unknowns. So, there's no limit, I don't have to stop at 3, I can do more than 3, but I need at least 3 such measurements, and that's exactly the principle of phase shifting interferometry. You take a reading, introduce a known phase shift, take another reading, introduce another known phase shift, and you go on doing this. So, what does that allow you to do? My initial equation is this. Now, let's say we pick those known phase shifts not to be some random value, but some specific value, and let's say we use the values that I have listed over here. So, my initial expression is I naught plus I dash into cos psi of this, right? But now I am adding an extra psi, and I am adding, initially it is 0, so I have the original expression, then I add pi by 2, I add pi and I add 3 pi by 2. How will this expression change? What is cos of some angle plus pi by 2? Okay, what is it by plus pi? Minus, what is it by 3 by pi 2? All I am doing is changing my expressions like this. Okay. So, this means if I have when I say I have I1 of x of y, that means I have a camera image and I have the pixel information everywhere, right? This is my I1. And again for I2 I will have the same information, but of course the intensity now on each of those pixels is different. Okay. So, if I carry out the operation shown here, in other words, all I am doing is simple pixel subtraction and then dividing it by another pixel subtraction. What does this give me? What does I4 minus I2 by I1 minus I3 give me? Do it quickly and tell me. You will get nothing but the tangent. So, now you see, how do you remember why did we start this whole discussion? Yesterday we said there's so much information in phase, no detector measures phase directly, therefore we are going to do an interference and use the intensity of that interference pattern to extract phase. And this whole exercise from then to now has been, well, how do I get out phase? A single intensity pattern, a single intensity of an interference doesn't give me phase. In order to extract phase, I need to make at least 3 measurements mathematically, but you see if you make 4 measurements and you pick this as your phase shift, you then arrive at a very simple method by which to get the phase. Now I just have to measure 4 different patterns with my camera, do this pixel subtraction, put it into this formula, and then take the argument of those measurements, and I will get the phase at every point. Okay. You see any problems with this? Yes, no? Okay, we'll come back to that. So, people use, we know we need at least 3 measurements. There are a variety of algorithms out there starting from the minimum 3 to almost an infinite number of measurements. Okay. Why do you need to have so many options? You might think, well, 3 is what I need. I've just convinced you 4. I hope I've convinced you why 4 is good, makes things easy. Why do I need to do 5 and 6 and 10 and 100 and so on? It turns out that every algorithm will be sensitive to some errors more than others. Okay. Now, it always sounds nice mathematically. We did that little derivation and we arrived at tan phi in terms of those 4 intensity measurements you have made. But all of this rests on the fact that you are introducing a known phase shift. How accurately are you doing that? The moment you introduce a phase shift, and if you introduce an error along with that, you say I am introducing pi by 2, but it is actually pi by 2 plus some delta. That error is going to cascade into all your readings. You may not be, in some cases, if you have a known fixed error, even an unknown fixed error, maybe it will subtract out. But it may be that the error has a range. Typically, the error will be, it will be anywhere between this and this value. So, every time you are introducing a slightly different error, you can't subtract it out. So, these algorithms will be more sensitive to some errors, errors than other errors. And since you can introduce that known phase shift in different ways, some methods will be more prone to creating some kinds of errors than other errors. So, people will do quite an extensive study to see what is the kind of method we are going to use, what are errors typical that are introduced by this method, what is the range of values of the errors introduced by this method, which algorithm will be least sensitive to these kinds of errors, and then you would pick that algorithm. Okay. Here are some examples of how you could introduce the phase shift. As the first thing that comes to mind always is just shift the mirror. Pi by 2, I mean, if I am talking about 633 nanometer wavelength, that means half of that length. So, you are talking about hundreds of nanometers is the movement required to do a pi by 2 phase shift. So, it has to be very accurate. So, usually you will have the mirror mounted on a piezo device and you are applying a voltage and it is moving through that distance. You could also have a grating, and do not worry about it too much, you can have a grating. When you move the grating, the phase in the order will change slightly, or you could also tilt your mirror to create a phase. There are other techniques too, these are some of the common techniques, right. In the fiber interferometer, it is quite simple to introduce a phase shift because you get a piezo cylinder with fiber wound around it, and you just splice this fiber into your reference arm, and then when you apply a voltage, that cylinder will contract and the fiber is wound very tightly around it. So, the length of the fiber also changes, maybe the refractive index also a little bit, and you can calibrate this to say for this voltage I get this phase change, right. So, it does not matter how you do it, there are a variety of ways of doing it, but to crack the problem of getting phase out of that interference pattern, you need multiple measurements and known phase shifts introduced between each of those measurements. Okay. Okay. There are in fact ways of also extracting phase without doing multiple measurements. Bhagat is working on that for his PhD, and maybe if you are interested you can talk to him about that. So, you can also just beat the whole system and say I will take one intensity reading and somehow extract phase from that. Okay. But for this class this is good to know, and this is actually a technique that many people still use. It's a standard, phase shifting is a standard technique. Okay. So, with that we will close this part and let me move to the next. So, are there any questions on this part? Okay. So, with this part you should have got a basic introduction into what is interference, what are the conditions for interference, why it is important, and how we actually extract phase. Okay. So, for the next few classes we are going to look at applications. Briefly I have mentioned some of the applications, I want to go into a little more detail. So, it should be fairly clear that I can use interference to tell if there is a difference between two wavefronts. So, I can extend this idea to say if I am interested in testing an optical element, the shape of that element, if light were to travel through or reflect off that element, the wavefront is going to change according to that element's shape. So, by studying the interference pattern, I should be able to say something about the element's shape itself. Okay? So, a Newton interferometer is used commonly for testing optical elements. Okay? How does a Newton interferometer work? I always need at least 2 beams. So, here's the source. Light travels through this source, from this source, through this beam splitter. So, it's not it's partly sending some light through. That light comes and hits this element here. Now, this actually is 2 elements. One is a reference, and on this you put your device under test. Okay, so, the device under test is resting on this reference surface. It has to be, it's an optical reference, it's called an optical flat. That means its surface has been polished to a very high flatness, okay, because we are worried about the variations in lambda. So, it's polished to a very high flatness. It's fairly easy to get optical elements with a roughness of less than lambda by 10, and you can, if you need to, you can even do lambda by 20. Okay? But so this is your reference flat, this lower, and this is the device under test. Okay? Where do I get the 2 beams from? I need 2 beams. It's a reflection measurement. So, the 2 beams of interest are coming here. Where are the 2 beams coming from? Reflection from this surface and interface. He says reflection from here and here. No, now he says here because he's psychoanalyzing my voice and saying, it doesn't sound right. Okay, I'll tell you, it is this reflection and this reflection. Okay, so the surface that we want to study is usually placed here. So let's say I wanted to study a convex surface, I would place it like this. Okay, but I'll turn back and ask you a question. Why am I not worried about this reflection? Your first instinct was to say that it's from there. So I can assume I have 3 beams coming back. Why am I not worried about 3? It doesn't matter, let it be there. Am I worried about the 3rd beam? Is it going to bother me when I try to analyze the surface? No, it's not going to bother me. That it does, it is a problem. I don't want it. I don't want that beam there. Oh, you haven't even answered this question. I have many more questions for you. Why don't I want that beam there? So first of all, this picture is not really drawn to scale. Okay? My reference flat and the surface or the device under test, then they will not be of the same thickness. Okay? So if I were to draw this to scale, it would be much more like this is the device under test and this is the reference. Why does that matter? Why does that make a difference? Remember, I said don't make the assumption if I give you 2 beams from the same source, you have interference. Do I always have interference? it needs to have coherence, and I've put monochromatic source up there. By the way, this is not a laser, okay. This will be something like a sodium vapor lamp or something, right. So, it's more monochromatic than the light you get from a tube light, but it's not a laser source, okay. So, it has a much shorter coherence length than a typical laser source, right. But by having this, so for I have a reflection from here, I have a reflection from here, these two beams must interfere for this system to be useful to me. That means a path length difference between the beam coming off the upper surface and the interface must be less than the coherence length, and the beam coming from here, this is way more than the coherence length. The path length difference is larger than the coherence length. So, it does not play a role in the interference. But can it still cause problems? Remember, if I have a good interference pattern, my visibility is going to be high, right. That means if the peak intensity here is some value I naught, this could even be 0 if I've got it perfect, right. But if I have another reflection coming in, some other light coming in, that light is not playing a role in the interference, it's going to create it's going to have some level here. It's like a DC light that exists everywhere. It doesn't play a role in the interference, but it will affect the contrast. So, I don't really want to have a reflection. So, one is I ensure that the reference flat is large enough so that if there is a reflection, it doesn't play a role in the interference. And secondly, I can make this region dark or black or absorbing so that I minimize the amount of reflection, okay. Okay. Now that I have these two beams coming back, what am I going to see? Remember, we are drawing it as lines, but actually that is why you have a diffusing surface there. It is scattering and making the beam larger. So, you are looking at a beam of some larger area, okay, because I need an area over which to see fringes for it to be useful to me. There is no point if it is lying within a beam of infinitesimal size. I must be able to see, okay. So, let us say this is the reference flat, and this is another flat. I am testing a flat, I want to make a flat. So, I place it one on the other. Now, to our eyes, it may look like these are placed flush against each other and there is no air gap, but that's never the case. There is always a gap, and it can, if you have not designed your flat accurately, if it is not flat, it could even have a wedge in it. So, when you place it one over the other, it may be that you have a wedge like this, okay. What kind of fringes are we going to see? What do the fringes look like? You are looking from the top, okay. So, this is a side view, and now I am asking you, look from the top. What are the fringes that you will see? Straight line fringes, right? Why straight line fringes? Because you have the reference wave, the wave coming off the reference flat is a plane wave, and the other wave is tilted, and you have these two waves that are interfering, right. So, you will have straight line fringes. There is a linear change in the optical path length. Now, you could, if it were as simple as this, you will say if the angle, the wedge is alpha, then the air gap is going to be alpha x, where x is this distance. Let us say this is x equal to 0, right. So, the alpha x at any height, this is alpha x, where if this is x measured from this origin as defined here, right. So, the optical path length then is 2 alpha x, because one wave travels to the lower surface and reflects back up. So, that is 2 alpha x, and I am telling you the dark fringes will occur here. Does that seem right? Why are the dark fringes occurring at n lambda? Doesn't that sound more like the constructive? Shouldn't you expect constructive interference? whenever you have a multiple of lambda. I am now asking you to go back and think about your electromagnetics. Light, after all, is an electromagnetic wave. It's hitting a dielectric surface. So you have air and you have a dielectric surface. What happens on reflection? There is a pi phase shift. So if you remember when you were studying boundary conditions and Fresnel equations, your Fresnel equations would have told you there's always a pi phase shift on reflection. On reflection, when you have air and some n which is greater than 1, then you have a pi phase shift. So there's an additional pi phase shift that's arising. When you count, if you look at this 2 alpha x, that distance, that's only taking a phase change that has occurred due to the path length. You need to take into account all of the phase changes to get the interference condition. So because of that extra pi phase shift, the dark fringes occur here and therefore the bright fringes occur here, but it doesn't matter. You take distance from one dark fringe to the next or from one bright fringe to the next. If you just take 2 alpha x is equal to n plus 1 lambda and 2 alpha x naught is equal to n minus, we can do that. 2 alpha x 1 is n lambda and 2 alpha x 2. So let's say this is the location, this is x1 and this is x2, right. This will be n plus 1 lambda, it's the next dark fringe, and if I take the difference between these two, so x2 minus x1, or the distance between them, is going to be nothing but lambda by 2 alpha. And that's true whether I take the distance between two bright fringes or two dark fringes. Okay. Okay. Let's say I had a flat, but the flat has a small depression in it, like here. Okay. So not a hole actually, it's a hollow. I would rather than say hole, I'll say a hollow. Or the flat has a bump in it like this. What will happen to the fringes now? If these were two flats on each other and we know there's a slight angle always between them, the fringe pattern is a set of straight lines in the region of overlap. But now in one area there's a depression or a bump. What will happen to the fringes now? Any idea? Everywhere other than this region, the fringes are going to look the same, right? Now somehow these fringes have to connect. The fringe above this hollow and the fringe below this hollow. It will connect along the path where the optical path length difference is the same. So if you look at the fringes, they'll look something like this. Okay. So you can actually use this to tell whether you have a depression or a bump in your optical flat. Why is it? You might, you know, the way they make these flats is by grinding. So you need to find out if in some region it's not been ground enough. You need to know where, and you have to grind that region or do you have to grind the region around. So if it's a depression, you have to grind the region around to make it all flat. If it's a bump, you need to grind in that region to flatten that region. So you need to know that. And this is the Newton interferometer is a very easy instrument to use. There is no alignment because the path length difference is so small. You are not aligning anything. You are putting your test element there, and the reflection from the top and the bottom of this element is what is interfering. Right? And you just visually are looking at the pattern and deciding what to do. Okay, so it's a tool that was used a lot earlier when a lot of the grinding was done manually. people would be doing the grinding, they'd put it there, they'd look at the patterns, and then they'd go back and know where to grind it. Now, of course, a lot is automated. But you would still use such interferometers and then be analyzing the fringe pattern and telling the machine what to do or where to do what. Okay. So, what happens if my device under test, the element under test is not a flat but a curved element? Say you are making a convex lens. What do the fringes look like over here? So, again it is always controlled by this path length difference, and I can calculate if this is part of a sphere, if this is part of a sphere, then the sag is going to be determined by the radius of curvature of the sphere and the location from the center by this expression. And again is an air glass reflection, so there is an extra lambda by 2 path length I have to think about, or that pi phase, and so the dark fringe is going to occur in this region. Okay. What do the fringes look like now? If there were two it is going to be a set of circles, concentric circles, right? And not only does it tell you, so the fringes, just by having a look at them, you get an idea of the surface, but the number of fringes is also telling you something, because you know each fringe is happening at lambda by 2, right? So, 4 fringes means you have a 2 lambda deviation. So, you are even getting an idea of the actual path length difference. So, it is not just the shape you are getting, you are actually quantifying to some level. And usually people measure from dark fringe to dark fringe rather than from bright fringe to bright fringe, and that is because it is hard for us to accurately find the center of the bright fringe, where your detector might even be saturating over that region and you are not able to locate the center of the bright fringe, but the dark fringe null is, and more accurate measurement can be made of it. Okay. So, although bright fringe to bright fringe or dark fringe to dark fringe distance is the same, most measurements are made using the dark fringe. Okay. You can go a step further. You can say that, well, if it's if I have a sag of lambda, I can see a fringe. But say the sag is less than lambda, what do I do? Right? Say this optical path length is less than lambda, how do I make it? Then I am not going to get a full fringe. I need a full fringe in order to, so I need an optical path length to be at least a full fringe in order to see the fringes, right? So, you can move your test object, you can move it so that you introduce extra path length, and that is what they show over here. If this distance were less than lambda by 2, I am not going to see a fringe, but I can tilt it. So, I am basically pressing down on this side here. Okay, and this is an exaggerated figure, you are not going to make it of course so large, it is going to move up a little bit, but that is going to add those extra lambdas in the path length. So, you will have extra lambdas here, right. And if you are doing this in a known way, you then can say that I've applied this much pressure, then you see these fringes and you will get some idea about the type of, right. So, you could either just use it not to quantify, but to qualify, is it a spherical surface, is it a flat, or so on, from the nature of the fringes you get. If you get straight line fringes, then you know that it is a flat, for example. Okay. So, you can use it to qualify, not quantify things. Okay. How do I know whether it is convex or concave? Whether it is convex or concave, I am going to get concentric fringes. How do I know whether it is convex or concave? So, again I will use movement. So, if initially I have placed it like this, what you can do is press down here. Now, when you press down here, the center that was originally here has moved here. So, your fringe pattern will also move. So, the center of your fringe pattern moves. So, if you are applying pressure on the left and the fringe pattern moves to the left, then you will say you have a convex surface. On the other hand, if you press on the left and the fringe pattern moves in the opposite direction, then you know you have a concave surface. Or you could say I will press in the center, and if you press in the center, what happens to this fringe pattern is you are slightly squeezing it down. So, the fringe pattern will expand. So, if the fringe pattern expands, then you say it is convex, and if the fringe pattern contracts, then you will say it is concave. So, just an observation of fringes or how they behave when you tilt this element or move this element can give you an idea about the nature of the element. Okay. Okay. So, we started looking at applications, and we have seen how an interference pattern can allow us to very quickly tell something about the shape of an optical element, and we will look at more applications in the next class.